Okay, so the complex number omega where omega is not equal to 1 is a root of this equation, z cubed minus 1 equal to 0. Part A, show that 1 plus omega square is equal to 0. Okay, so there are a few ways you can do this question. I personally like this way that I'm going to show you. Okay, but there are other methods to this. So we look at 1 plus omega square. And we note that this is actually a GP. Okay, it's a GP, common ratio omega. And number of terms is 3, right? 3 terms. So the sum of these 3 terms will just be 1 times omega cubed minus 1 over omega minus 1. Okay, making use of the GP formula. But well, we know that omega is a root of this equation, okay? So that necessarily means that omega cubed minus 1 equal to 0 because it satisfies the equation. Okay, which also means that omega cubed is really equals to 1. Okay, and here we have it, omega cubed over here. So this can be replaced by 1 minus 1 over omega minus 1. And so this is going to give me 0. Okay, I don't need to really bother about what omega is. Okay, the other method, okay, method 2 is to figure out what omega would be. Okay, so since omega is a root of the equation, we know that omega cubed equals to 1, like what we've pointed out. Okay, but using what we've learned in the earlier chapter, this is e to the power of I 2k pi. And so we get omega equals to e to the power of I 2k pi over 3. Now k is only going to be 1 or 2, okay, because as we have learned, we have found out earlier, k cannot be equal to 0, right, since omega is not equal to 1. Okay, if we let k equals to 0, okay, we will get, e to the power of 0, which is 1, okay, and that's not what we want. Okay, so then you have to kind of like say it. So say omega is equals to e to the power of I 2 pi over 3, right, which is cos 2 pi over 3 plus I sine 2 pi over 3. Then what is 1 plus that? Okay, so you kind of have to whack it out, okay? Do it out and figure out what this expression is. 3 square. Okay, so work it out and show that it's equal to 0. Now, I personally prefer the first method, but if you think the second method is better for you, please go ahead and learn it. Okay, now part B. Hence, now show that 1 plus omega to the power of k plus omega to the power of 2k, where k is a positive integer, is not 0, where k is a multiple of 3, but 0 when k is not a multiple of 3. Okay, now, regardless of whether k is a multiple of 3 or not, we know that this is still a GP. Okay, common ratio now no longer omega, but omega to the power of k. Okay, and we have 3 terms. Okay, so now the only thing is the whether or not k is a multiple of 3 or not will affect the value of this omega to the power of k guy. Okay, so we need to kind of consider it carefully. So since we have that hint, let's consider it separately. So case 1, if k is a multiple of 3, okay? If k is a multiple of 3. So if k is a multiple of 3, then omega to the power of k can be written as omega to the power of 3 times some integer n, right? Because k is a multiple of 3, as we've learned, means that I can write k equals to 3n. Okay, where n is now just any ordinary integer. Okay, so, but omega to the power of 3 is 1. Okay, because of this results, okay, because of this omega to the power of 3 equals to 1, just to remind you. So this is going to be omega cubed to the power of n, which is 1 to the power of n, which is equals to 1. Okay, and so now the common ratio is actually equals to 1. We're not going to be able to use the GP formula, okay, to find the sum of the GP. So, but that's okay because, well, omega to the power of k is just 1, no matter what, and omega to the power of 2k would also be 1. So, therefore, 1 plus omega to the power of k plus omega to the power of 2k is just 1 plus 1 plus 1 equals to 3, which is not 0, okay, when k is a multiple of 3. Now, case 2, if now k is not a multiple of 3, okay, if k is not a multiple of 3, well, then omega to the power of k is not going to be equals to 1. Okay, well, it's quite clear from the context. Okay, earlier when k is a multiple of 3, omega to the power of k is equals to 1. So now when k is not a multiple of 3, okay, we won't get any interference, okay, into the value of omega to the power of k. It won't be 1, and so we do have a legitimate GP. Okay, so now I have 1 plus omega to the power of k plus omega to the power of 2k is a GP, okay, with some common ratio omega to the power of k, and that will give me omega to the power of k to the power of 3 minus 1 over omega to the power of k minus 1 as a GP. Okay, but unfortunately we're not out of the woods, because in the numerator we still have omega to the power of 3 to the power of k minus 1 over omega to the power of k minus 1. And since omega to the power of 3 is still equals to 1, okay, we have 1 minus 1 over omega to the power of k minus 1, which is still equal to 0.